For our Chapter 12 review number 3, we're starting off with a very involved problem. Take a look at number 1. f of x is the sine of 5x plus pi over 4. We're asked to make a Taylor polynomial for f about x equals 0. You can very well say this should be called a Maclaurin polynomial. The College Board very often does not distinguish between a Taylor series or a Maclaurin series. Very often Taylor is used for both. But regardless, take a look at the top of the screen. I think one of the biggest questions kids tend to wonder about is, with this very famous Maclaurin series that you should have memorized for sine, is it possible to substitute in wherever you have an x, simply replace with 5x plus pi over 4 and get a new series? The honest to goodness truth is you can always do that, and you can see I've done that up here to get this true statement that the sine of 5x plus pi over 4 is equal to 5x plus pi over 4 to the 1 minus 5x plus pi over 4 all raised to the third over 3 factorial. This is definitely a true statement, but the question is this the answer to part A if we were to go up to just the third degree? The answer is no. Even though this substitution is a correct substitution, it is valid, if you look very closely, you're going to see that we do not have a series about x equals 0. We don't just have x minus 0 raised up to different powers. Many kids on this AP exam made that mistake in the past, and that, of course, is not following the directions as to what we're asked to do. That begs the question then, so how do we make a third degree Taylor polynomial? Answer is pretty much with brute force. Taking f of x is your sine of 5x plus pi over 4. Of course, what we'll do is we're centered at 0, so we'll plug in a 0. We'll just have radical 2 over 2. The sine of pi over 4 is simply that. As we take our next derivative, or the first derivative, you're going to see the derivative of sine is cosine. But please watch out. The chain rule is in effect. We have to take the derivative of 5x plus pi over 4, or we're going to get a 5 to come out. So f prime of 0, the cosine of 5 times 0 is 0, 0 plus pi over 4. Cosine of pi over 4 is root 2 over 2, but don't forget you have this 5 out in front. Then we're going to take a second derivative here. The derivative of cosine is actually negative sine. So we'd get a negative, another chain rule, we'll have another 5 come on out, and we'll have negative 5 squared sine of 5x plus pi over 4. And you can see as we plug in a 0, we'll be left with negative 5 squared, which of course is negative 25, but the sine of pi over 4 is just going to be root 2 over 2. Now we're asked to go to a third degree, so we should go out to that third derivative. And the derivative of sine, of course, is cosine. We're going to have the chain rule in effect one more time. So we still have that negative out in front. But, of course, as we substitute in a 0, you're going to see once again the cosine of pi over 4 is going to be root 2 over 2. You can see that we've just gotten one more factor of 5 out in front. Now it's very tempting to stop here, but if we read ahead a little bit, you can see at the top of the screen it says use the Lagrange error bound on this polynomial. We're going to try to measure error. And to be able to do that, we're going to have to go one further derivative. Derivative of cosine is the opposite of sine. So a negative comes out. We're going to have a 5. We have one more factor of 5 coming from the chain rule. But with the Lagrange error bound, Remember that this is where we don't plug in where we're centered. We actually plug in this very abstract z. So we'll have 5 to the 4th sine of 5z plus pi over 4. And of course, we're going to need this relatively soon. Well, as we're looking ahead here for part A, this third degree Taylor polynomial about 0 would be f of 0 plus f prime of 0 x to the first plus f double prime of 0 x to the second all over 2 factorial plus f triple prime of 0 x to the third all over 3 factorial. And, just making these substitutions in very quickly, you can see we'd have radical 2 over 2. Here we're going to have 5 radical 2 over 2 x to the first. As we go to our second derivative, you can see we're going to wind up with something negative, a negative 25 root 2 over 2. But we're going to divide by another 2 or multiply by another 1/2. So we'd have negative 25 root 2, but another factor of 2 will show up down below. We'll have that 4 down there. And then finally with this third derivative, you can see negative 5 to the third is actually negative 125. And we'd have our radical 2. But 3 factorial is actually a 6. And the 6 times the 2 in that denominator becomes a 12. So this is our answer for part A. By the way, they certainly did not ask for this, but we're going to need this for part C. The Lagrange error bound, if we were looking at that, you can see we had 5 to the 4th. 5 to the 4th is going to be 625. So we'd have 625 sine of 5z plus pi over 4. And then, of course, we're going to have our x to the 4th all over 4 factorial. We're going to need that later. So just wanted to jot that down very quickly. As we take a look at part B, however, looking at part B, it says find the coefficient of x to the 22nd in this Taylor series. And thank goodness you certainly do not have to go ahead and make 22 consecutive derivatives here. But I hope you can see some patterns. Look at this. With our first derivative, we had 5 to the first. Second derivative, 5 to the second. Third derivative, we had 5 to the third. We're always going to have a root 2 over 2. But adding to some confusion, you might think, well, now wait a minute. Sometimes our terms are positive. Sometimes our terms are negative. So there's more to the story here. We know we're going to have a root 2 over 2 for our 22nd derivative. We know we're going to have 5 to the 22nd. But the big question is, will we have something positive or will we have something negative? Now, as we're looking here, I hope you can see that any time that you're taking derivatives of trig functions, there are cyclical patterns. You can see that our 0th derivative is starting with sine. Then we went to cosine. Then we went back to sine. Then we went back to cosine. But you can see that we went from something positive to something negative, to something negative. And now once we get here, it's as if for that 4th derivative, we're right back to taking a derivative of a positive sign. So we're seeing a cyclical pattern, a pattern of length 4, really. And that's very typical of trig functions. You could say that this would be remainder 0, this would be remainder 1, this would be remainder 2, this would be remainder 3, if we were dividing by 4. If we took 4 divided by 4, we'd be back at remainder of 0. So the big question is, how do we know whether we have something positive or negative? Well, we're going out to that 22nd derivative. And if we divide by 4, 5 times 4 is 20. 22 minus 20 is a 2. We'd have a remainder of 2, as you used to write back in 4th grade. Remainder of 2 is right over here. We'd get something negative. We'd get something negative. Now, notice what they're asking for part B. They're not asking for, the complete term involving x to the 22nd. They're asking for the coefficient. The coefficient would simply be the 22nd derivative evaluated at 0 divided by 22 factorial. So we're really asked to work this out. We already know by this remainder of 2 that we should get something negative. So I know we'll have negative 5 to the 22nd. We'll have a root 2 over 2, of course. But what else? Down below, we're going to have a 22 factorial. And that is the coefficient, what is out in front of x to the 22nd. For part C, they're actually saying, please do work out this Lagrange error bound. And this is where we're going to go back really to our error with what I've written up in top. The error, of course, is going to be less than the Lagrange error bound. Now, we're trying to measure error at 1/10. By the way, whenever you see f of 1/10 minus p of 1/10, f of 1/10 is the true value, p of 1/10 is the estimate. The true value minus the estimate is the error. We're trying to show that our error is less than 1 over 100. So what we'll have here is plain and simply, this is 625 sine of 5z plus pi over 4. And then we'll have our x, which is going to be 1/10. This is 1/10 to the 4th. And we're going to say this is all over 4 factorial. Well, here's something that you need to know. Z is going to be between, it's greater than 0, but it's less than 1/10. But let's just say you don't even have a calculator here. And by the way, more and more, 2/3 of your free response questions now are no calculator allowed. And you might be thinking, is there a way we could do this without a calculator? Remember, we're trying to maximize this. A little trick that we can do is say, we know that the largest sine can ever get is 1. So we can know that this would be less than, whether you have a calculator or not, you can do this. It'd be less than 625 times 1 times 1/10 to the 4th. 4 factorial is 24. Of course, you could even work this all out by hand if necessary. And you would get 1 over 384. That denominator is larger than 100. So this would be enough work to justify what they're asking you to do. As we go to part D, it says, let G be this integral from 0 to x of f of t. Write the 3rd degree Taylor polynomial for G about x equals 0. Well, for part D, tell you what, I know we're going to go from 0 to x. For part A, you can see we wrote out a 3rd degree Taylor polynomial. And we're going to need some dummy variables in here. I'm writing down my answer for part A with dummy variables. But you see, this is a 3rd degree Taylor polynomial. It's part of that infinite expansion. And, they're asking us to integrate this really term by term by term. We're going to integrate this with the fundamental theorem. What's the antiderivative here? You'd get root 2 over 2 x plus 5 root 2